Hello, welcome to this one. In this one, we're going to go over the x64 equivalent of trampolines. So in the last video, we covered x86 trampolines, and today we're just going to show off the x64 sort of version of that. So there are a few little differences as we're going to go over now. Nothing too major. I'm not going to be writing the code in this video. I've already got a pre-made example, but we're just going to be talking over it and just sort of discussing the two main ways that we can go about doing it. So some key changes from x86. Obviously we're in x64, so we have 32 more bits to play with. So obviously with different points, different sizes in memory, things like that, things are going to change, such as pointers and in general just size, things like that. But it doesn't affect us too much in terms of hooking. There's just some things we've got to be aware of. So the main one being the relative jump. It can only jump to a 32-bit address. You can perform an absolute jump in x64 and x86, so you can jump to a static address as what we're, well, not a static address, but a defined location, as we're going to do in this through one method. But if we want to perform a jump, we need to be a bit closer rather than further away. So we can only jump to within a 32-bit address range, meaning if we want to use it, we must be located a bit closer to our function that we're hooking from, essentially. But what we can do is we can jump to an address stored in a register. So if we move an address into a register and then jump to that, that's going to work perfectly fine, which is one of the ways we're going to do it. So the first method I'm going to be showing is we're going to use the R10 register. We could also use R11. So these are both temporary registers and they're not used for function parameters or throughout the function lifecycle. They're not going to get impacted by the flow of execution, things like that. So these are the two safe registers to use in x64. And we can use either one of them. We could use R11, in this case we can use R10, but it's just an example of why you wouldn't use certain ones. If you want to know a bit more, if you want MSDN and look up the x64 registers and the calling conventions, things like that, it'll explain why. But registers R9 through to R12, I believe, are all used in function parameters, things like that. R10 is not, neither is R11, so hence we're going to use those. Yeah, so if you use any other registers, just be aware it can mess things up, so it's just better to play it safe and just use ones that aren't going to be touched by any sort of code or anything like that. So it says there, if we use it, it's not going to impact our program execution, which is the main reason why we are using or deciding to use these registers. So how it's going to actually look from more of a diagram or visual format is pretty much the same as our old sort of method, except this time it's just going to take up more space. Obviously, because we're x64 and not x86, so a pointer in x86, obviously you got 32 bits, it's going to be 4 bytes. Whereas in x64 it's going to be 8 bytes. That's why size and things like that's going to change. So our function pointer takes up 8 bytes, and then obviously our instructions will take up the remaining 5, and in total that gives us the 13 bytes that we need. So what that basically means for us is if a function is smaller than 13 bytes, we can't hook it, essentially. Or if it is 13 bytes, we're probably not going to be able to hook it. That's sort of a space limitation there. This is why this method's probably not ideal if you're using sort of smaller functions that are just sort of helper methods, things like that. So whereas if we're just using a jump instruction, we can hook it using 5 bytes, or in some other ways we can actually hook it in smaller methods as well. But obviously that's one major limitation of this. Now personally, I don't mind using this method because if you're going to be using it on any sort of decent function, let's say DirectX, or some sort of graphics library, you're always going to be able to fit this in. It's always going to work, but it's just consideration to be aware of the size difference. But this is where the next method that we're going to use comes in. So now, let's say we've gone to a function and we need we need less than 13 bytes. Because as you know anyway, if we're going to hook a function, generally it's not always going to fit in that 5-byte range. Maybe it might be 6, 7 or 8, or maybe even 10, something like that. So you've always got a bit of room to play with, but just in case we haven't, we need to sort of figure out another way to do it. So virtual alloc allows us to specify an address that we could try and allocate memory at. It doesn't necessarily mean it's going to work, but it allows us to do it so we can sort of iterate through that and find an address where it's close enough so it's going to work. We need to determine an address which is within a 32-bit range from our that's a spelling mistake, from our existing source function address, and to achieve this we'll write a wrapper around virtual alloc, and we're going to use this to create a code cave. This is going to be one of the code caves, and this code cave is then going to jump to our destination function. As we know from our last video, a code cave is just some allocated portion within a module, so it's just some memory basically. As you can see, another visual example. So we're going to go from our original function through our 5-byte jump instruction to a code cave that is allocated within that 32-bit range, and then with from that code cave we're going to go to our destination function. This is just going to be using our typical like absolute jump, so 13 bytes, don't really matter, we can do it however we want in this code cave as long as we've got the room. And then from the destination function we're going to jump to another code cave with the stolen bytes, and then that's going to start jump back to the original function. From the original code cave, it's essentially the same as the original trampoline, just with one extra step. There are a few ways we could improve this, but just in to a time constraint, and obviously I don't want to make it too overcomplicated, I like to do things that was the simplest way possible. We could make this a bit more efficient. Obviously, if we're creating 2 code caves, things like that, what we could do is create one big code cave and put our code in there, and just separate out the address and things like that. It's just something to be aware of, just one little optimization we could make among others as well, but it's just always something for you to be aware of. If it's something you want to try, when you go back and try and do that, basically allocate one portion of memory, put both these in and get it working that way. See if you can do something to achieve that, or I don't know, nice little challenge for you. Right, so here in Visual Studio, I'm just going to go through the code. I'm going to talk through it line by line, and then we're going to show it through a debugger as well, just so we can walk through it and make it a bit easier. So we have our test function here, and then we have our hooking function here. As I've said, this remains exactly the same if we were going to use it from separate modules, so if we're going to inject DLL into that, and another process, things like that, or either way you want to do it, if you want to do it externally, it remains the same, but obviously just for ease of use, I'm just demonstrating it in one module, but yeah, the process is the same, and if you can't figure that out, probably shouldn't be doing this, probably want to take a step back and then, yeah, reevaluate. So all we're doing is just inserting a trampoline, and these are our 2 methods that we've just discussed here. The insert trampoline 64 function is just your 13-byte, and then obviously your 5-byte hook is the trampoline 64 close. So yeah, nothing too major, no function parameters, things like that, but again, it remains the same. Match the calling convention, match the parameters, and you're not going to have any problems. I didn't mention this in the last video, but I should mention it now, obviously. If you're not matching your things like your calling conventions and your parameters, you are going to run into issues with the stack, and your program's just going to crash. It's pretty easy to fix, pretty easy to debug, but it's just something to be aware of, especially if you're using it in different modules. And just another little tip for people that are new to this: if you're always making a hook, and even if you're absolutely certain it's going to work, just build it in your own sort of, like I've done here, in somewhere you can control, where you have full debugging capabilities, and it will save you a massive headache and a lot of time. So all I do, even if I know code works, or if I'm absolutely certain, I'll always test it if I'm having issues in my own sort of environment, rather than going straight into another process or another game, because it can be an absolute headache, but just something to be aware of. So the first function we'll look at is just the insert x64 hook, which is essentially just like a place jump function before. This is just going to be the function that's going to place the jump from a function to another. It's not a trampoline, it's just placing a jump instruction essentially. So as you can see, starting off with our virtual protect, just so we don't have an access violation, so we can actually access that portion of memory. This is going to be the instruction that we're going to use, the R10 register. So all we're using here is creating a buffer with the certain instructions in. So move R10, and then our address is here, which we're going to copy into this buffer in a minute. And then finally the jump instruction here, we're going to jump to R10. So we're going to copy over the address of the destination register here back into this buffer. Copying the stolen bytes for later usage via trampoline, because obviously we need to execute those so the stack doesn't break. And then we're going to copy the instructions over that we've made up here, so I jump and move R10, and then in case that we've overwritten more than 13 bytes, we're just having a little pad in here at the bottom to ensure that everything matches up alright in our function. And then finally we're just going to restore our access permissions or access rights. The insert x64 hook close is a little bit different. This is the sort of the equivalent of the 5-byte. I think it's the exact same as our x86 version. I don't think there's anything too different in here, so I'm not going to go too much into this, but yeah, it remains the same as the x86 version. So access rights, copying our stolen bytes for later usage, inserting a jump instruction at our source function, and then we're just calculating our relative address. As we know, it's function B minus function A minus 5, obviously, for the jump instruction and the relative address there, or the address they're going to, sorry. And then finally, obviously, if we need padding in case we need it, same as before, we're just inserting some NOPs in there. So yeah, nice and easy. Actually, the trampoline sort of method in x64, as I said before, a little bit different. So right away, same as before, creating a stolen bytes buffer, we're inserting our x64 hook. So this is going to be the move R10 instruction, the 13 bytes. and then we're creating a code cave that's going to jump to our original function back, copying over the stolen bytes, and then we're going to have another jump to our original function, and we're inserting that after our stolen bytes. Copy just function into instruction buffer. There we go. Pretty much the exact same as our x86 equivalent, except this time we're just using 13 bytes instead of 5. Essentially, there's nothing too much different here. And then for obviously the usage of that, this is our example here, insert trampoline 64. So obviously we're going to insert it at our source function, go into our destination function, and the size of the hook we want to use, which obviously we'll go into a debugger and check if we're unsure. And all that's going to do is just take this function pointer, and then we're going to execute this function pointer at the end of our hooking function, so it automatically just returns execution to our original function. That's just a nice clean way of doing that, so we haven't got to do anything funky or majorly complex there. And finally, going into our second method of doing things, the insert trampoline 64 close. This is where we're going to use our rewritten sort of virtual alloc function, if you will. So right away, a little bit different. We're creating our code cave using the custom virtual alloc 32 function, which I'm going to go over here now. It's very simple, probably could be a bit better, but it does the job, so I'm happy doing it. So we're going to use get system info, and the reason why we're going to use this is because we need to know the maximum application address range that we're going to be using, so the minimum and maximum as well. So we don't want to be going outside of these parameters, because obviously if we go outside of one of these addresses, we're going to get an access violation, so that's why we need to know them. And then all we're checking for is if we're within this address range, so if we're outside of the if we're inside the minimum address and we're inside the maximum address, we know that we're in safe memory. And then we're just going to try and allocate memory within the process. If it can't do it, it's just going to do it again. And obviously we're just using an offset here, just so it keeps multiplying by the size. We could do this by pages, things like that, but I prefer doing it just this way because there's sort of a lot more to work with. We could make it a bit more efficient, I guess, if we do it per page, but virtual aloc's automatically going to go right down to the nearest page anyway, so I'm not too bothered. It's working fine for me. And obviously, if it's not going to return, we just get a null pointer there at the bottom. So that tells us that nothing's been, it's not found anything through the whole module. So yeah, could do a check in there if you wanted, if it's going to be 0, but generally you're always going to find somewhere in a process that you can go to, or potentially in this case maybe not if it's within 32 bits, but I highly doubt it, just in case, just something to be aware of if you want to do a bit of error checking there. Once we've created that code cave, we're then going to insert our hook close functions. This is, as I said before, it's the exact same as x86, our relative jump. So we're going from the source function, instead of going straight to our destination function, we're going to go back to the code cave, and then the code cave is going to jump to our destination function for us. So as you can see here, once that code cave has been created and the jump's been inserted, inside the code cave we're going to create a jump to our destination function down here with this buffer, the same as we did before. So copying the address of the hooking function into the buffer there, and then we're going to copy over the buffer to our code cave there, and then obviously we're just restoring the protections down here. So the code cave for jump, that's just printing out the address where our code cave to our destination function is going to be. And then finally we're creating a code cave for our stolen bytes, and I jump back to our original function, which is again nothing too complex. So a little bit different. A hook size is going to be a little bit different for this time. So we want the original hook size obviously for our stolen bytes that we're going to need, and then also we want an extra 13 bytes for our jump back to the original function, because we can sort of jump anywhere in a x64-bit range using absolute jumps. That's why we're going to use the 13 bytes, just so we're not limited to that 32-bit region. That's what the original code cave's for, so we don't have to be located within that initial region of memory. We can put our code cave anywhere and just jump to it as long as we get that initial code cave set up within the 32-bit range. And that's just the address of the code cave to the jump back to the original function, and then rinse and repeat, just create another buffer, and we're just going to jump back to our original function there. And then finally we're just going to return the address to that code cave, so we can specify that as our return address from our function. So I'll show off the 5-byte hook first, and we'll just go through it in Debugger, and then we will oh, wrong one, I can't see, there we go. So we'll open this up in x64 debug, and then we will go through the 13-byte hook. So this is the 5-byte version I've just said. So if we look here, in total, we've had to replace 10 bytes because obviously the instructions do not quite match up there. So obviously if we go in, or if you can't see now, but this basically went over a portion of, like, I believe it was 4 bytes, and then it went straight to 10. So obviously the instructions ran over, so that's why, hence why I've had to replace 10 bytes here. So if we just put a breakpoint on that, and now when we execute through our loop, here we go, we'll step into it and we'll go through everything here. So this is the code cave that's going to jump to our destination function. There we go. Look at that, it's going straight to our hooking function. And then from our hooking function, it's just going to go back to our other code cave. It's going to return back to our function. Oh, has it decided to chin me off? I think it has. We'll put a breakpoint on the other code cave. There we go. There we go. So this is the code cave with our jump back to our original function. So if we just step through this, eventually it'll execute back where we want it. There we go. So this has gone from our hooking function. This is going to go back to our original function now. So we step through this, should return back to our original function. And yeah, here we go. It's turned back to us after the jump instruction here. Obviously, if we didn't place this jump to back after this address here, we would just get an infinite trampoline loop, something I had earlier on. But it's just something to be aware of. There we go. We'll just disable this breakpoint so we can just sort of show it's working. So as you can see there, it's going through our hooking function, and it's also executing our original function as well, as any trampoline should. Nice and easy, and that obviously just takes up, well, 5 bytes, or it's the smaller hooking version, if you will. Whereas this next one we're going to show off, it will take up a minimum of 13 bytes to achieve. There we go. As you can see, all working as before, and again we'll just step through it. Trampoline x64, test func. Here we go. So as you can see in total, this one takes up a few more bytes there. So again, we'll place a breakpoint on it and we'll just step through it again. There we go. Jumping straight to a hooking function, pretty much the exact same as our original hook, except it's just going to take 13 bytes. There we go, and this is where it goes into our code cave, and as you can see there, another 13 byte jump there that's going to jump back to our original function. All there. Not a great deal to it. It's just obviously a little bit different. Obviously, it's good to know most modern games or modern applications are going to be in x64. There's nothing wrong with writing things in x86, so a lot of malware is typically a bit easier to write in x86 depending on what you're trying to do. So if this is your kind of thing, then obviously you're going to want to stay in x86. But when you're interacting with things that are in x64, these are going to definitely be good to know, especially from a game hacking perspective. Things like that with a lot of modern engines. There's no modern engine or no modern system that's going to use 32 bits, so it's always good to know. As always, I'll link the article and relevant resources in the description. Any questions, anything like that, please leave them in the comments, and thank you very much for watching.